In this week's lab, we're going to be looking at the forces that affect the stability of a slope. How stable is a given slope, and how likely is it to become unstable, resulting in slope failure, some form of mass wasting such as a landslide or debris flow. Questions that we want to address are how stable is a particular slope, and how likely is it for that slope to become unstable? How sensitive is the slope to some disturbance that affects its stability? We're going to get answers to these questions by calculating and evaluating the relative magnitude of the forces acting on the slope. Forces that resist movement or promote stability are called resisting forces. Forces that promote movement are called driving forces. Forces that promote movement make the slope unstable. We're going to evaluate the relative size of the resisting forces and driving forces acting on a slope, and then examine how likely they are to change. How close is the slope to failure, and what might affect the stability of the slope enough to make it unstable? The primary stress acting on a slope is the pull of gravity exerted on the material that makes up that slope. We can calculate that stress as the product of the thickness of the slope material times its density. In other words, what is the slope made of and how thick is that material, times the constant g, acceleration due to gravity. That gives us a stress on that slope due to the downward pull of gravity acting on the material that makes up that slope. In this particular example, we have 3 meters of slope material that has a density of 2,200 kilograms per cubic meter. G is our constant, 9.8 newtons per kilogram. Keep track of your units. Kilograms cancel. This meter cancels one of these. Our answer is a stress or force in newtons applied over some surface area, in this case square meters. 3 meters times 2,200 kilograms per cubic meter times 9.8 newtons per kilogram. We find that our stress due to gravity is 64,680 newtons per square meter. Notice that only part of that stress is directed parallel to the slope and promoting downward movement of that material. The other part of that stress is directed perpendicularly into the slope, holding the slope material in place and in contact with the underlying bedrock. So only part of the stress exerted to gravity is promoting movement. The other part is resisting movement because it's holding the material in contact with the underlying bedrock. We need to evaluate the relative magnitude of these two components, which is a function of the angle of the slope. The steeper the slope, the larger the slope angle, the more of that stress is directed parallel to the slope, which promotes movement, and the smaller proportion of that stress is directed perpendicular to the slope, which is resisting movement. We can resolve our stress due to gravity into two components using some simple trigonometry. Ratios between the sides of a right triangle. We have part of the stress directed parallel to the slope, that is a driving force, and part of the stress directed perpendicular to the slope, that is a resisting force called the normal force. Normal, as the name implies, is perpendicular to the slope. So we have a right triangle here. That means the relative magnitude of the driving and resisting force, the vectors, can be calculated using trigonometric functions like sine and cosine that relate the sides of a right triangle. Now, because of the congruence or symmetry of angles in a right triangle, this angle, the slope angle, is the same as this angle. The driving force, this vector, is therefore given by the sine of the slope angle. The resisting force, the normal force, this guy, is then given by the cosine of the slope angle. Because sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, that makes the driving force parallel to the slope a function of the sine of the slope angle, and the resisting component normal to the slope is a function of the cosine of the slope angle. Let's find the driving force first, the component of the stress due to gravity that's directed parallel to the slope and promoting downward movement. Our slope angle is 30 degrees. Sine of 30 degrees equals 0.5. We have 0.5 times 3 meters of slope material times with a density of 2,200 kilograms per cubic meter times G, 9.8 newtons per kilogram. Kilos cancel. That cancels one of these. Our resulting answer is a stress in units of newtons per square meter. 0.5 times 3 meters times 2,200 kilograms per square meter times 9.8 newtons per kilogram. Our driving force is 32,340 newtons per square meter. And again, the relative magnitude of the stress due to gravity that's parallel to the slope is again a function of the slope angle. As the angle gets larger, sine gets larger, and more of the force is parallel to the slope. As the angle gets smaller, the sine gets smaller, and so a smaller component of the total force is directed parallel to the slope. Resisting force, in other words, the normal force, perpendicular to the slope, holding the material in place, is given by the cosine of the slope angle. The cosine of 30 degrees is equal to 0.866. We take that number times thickness of the slope, 3 meters, times 2,200 kilograms per cubic meter, the density of the slope material in this example, times the constant G, 9.8 newtons per kilogram. Kilograms cancel. That meter cancels one of those. The resulting answer is a stress, units of newtons per square meter, 0.866 times 3 times 2,200 times 9.8, 56,014 newtons per square meter. That's cosine of 30 degrees times 3 times 2,200 times 9.8. The normal force is just one part of the total resisting force. There's an additional component due to the cohesion of the slope material itself. Cohesion is, of course, the ability of the material to stick together. That is resisting movement. So our total resisting force then becomes our normal force, which we just calculated, 56,014 newtons per square meter, plus the cohesion of the material that makes up this particular slope. In this example, it's 1,100 newtons per square meter. Same units, we can just add these together. Our total resisting force becomes 57,114 newtons per square meter. Factor of safety is a measure of how stable the slope is. How large are the resisting forces relative to the driving forces? As resisting forces get larger and driving forces get smaller, factor of safety becomes larger, and the slope is more stable. But as driving forces increase, resisting forces decrease, this number gets closer to 1, the slope becomes more likely to fail. We would not expect to see a factor of safety less than 1, because that would mean that the driving forces are larger, the resistance forces are smaller. Such a slope would be unstable and wouldn't exist. Mass wasting would occur, landslide, debris flow, or some other mass wasting process, reducing the magnitude of the driving force, increasing the magnitude of the resisting force, and making the slope stable again. So factor of safety, the bigger it is, the farther from 1, the more stable the slope is. As factor of safety approaches 1, slope is becoming unstable. Mass wasting is becoming increasingly likely. What is the factor of safety in our example? We had our total resisting forces, 57,114 newtons per square meter. Our driving forces we calculated to be 32,340 newtons per square meter. Units are the same. Dividing them cancels, so factor of safety has no units, it's just a ratio. 57,114 divided by 32,340. Our factor of safety is 1.77. This means that resisting forces are 1.77 times larger than the driving forces. The slope is stable. Resisting forces are almost twice as large, 1.77 times as large to be exact, as the driving forces are. Next step, which we're going to do in the second part of this week's lab, is to think about what changes could occur to the slope that would affect the factor of safety, that would affect how stable the slope is. Is there something that could cause the slope to fail? Is there something that would increase the driving forces or decrease the resisting forces enough to bring the factor of safety to 1 and make the slope unstable? We'll examine how sensitive our slope is to changes in cohesion, which is a function of the type of material that makes up the slope. We'll examine what happens when the slope gets wet. Presence of water reduces the normal force because it exerts a pore pressure on that slope material. And we'll calculate how changes in the slope angle affect the relative magnitude of driving and resisting forces. Naturally, increasing the slope angle makes the driving force larger, resisting force smaller. And the opposite is true of reducing the slope angle. We want to see how sensitive our slope is to a disturbance. We're going to change one of these components at a time: slope cohesion, water content, or angle, and see how that affects our factor of safety. how that change affects the ratio of the resisting forces to the driving forces. How sensitive is the slope to this change? Let's first look at cohesion. We had an initial cohesion of 1100 newtons per square meter. What happens if the cohesion goes to 0? This would occur if the slope is subject to shaking during an earthquake. How sensitive is the slope to a loss of cohesion? Well, driving forces remain the same. Our resisting forces remain 56,014. We're no longer adding 1100 newtons per square meter. So our total resisting forces are 56,014 newtons per square meter divided by our driving force. Again, we calculated before, 32,340. Our factor of safety, if cohesion goes to 0, is 1.73, which is a reduction from the 1.77 we calculated earlier. So letting cohesion drop to 0 affects the slope stability, makes it more likely to fail, but not by much. The slope is not particularly sensitive to a loss of cohesion. What if cohesion goes the other way? What if we change the slope from loose sediment to solid bedrock, which increases the cohesion dramatically? How does that affect the factor of safety? Well, naturally, it's going to make the resisting forces larger. Our original cohesion, 1100 newtons per square meter, make it 1,000 times larger, multiply by 1,000. We now have 1.1 million newtons per square meter plus our normal force, 56,014. Our total resisting forces are 1,156,014 newtons per square meter divided by our driving force, 32,340 newtons per square meter. Our new factor of safety becomes 35.75. Slope is now extremely stable. Resisting forces are almost 36 times larger than the driving forces. A slope composed of solid rock is a lot more stable than a slope composed of loose soil or sediment because the cohesion of rock is much higher. What about adding water to the slope? When we add water to the slope, what we're doing is reducing the normal force by an amount equal to the pore pressure exerted by that water. In other words, we're reducing the normal force by an amount equal to the force exerted by having our pore spaces filled with water rather than air when the slope material is dry or unsaturated. Let's do an example. We have our 3 meters of slope material. Let's saturate it with 1 meter of water. How does that change the normal force and the factor of safety? Reduce the normal force by the pore pressure exerted by that water. It's given by the density of water, 1,000 kilograms per cubic meter, times the amount of material that's saturated, in this case, in this example, 1 meter, times G, 9.8 newtons per kilogram. The pore pressure exerted is 9,800 newtons per square meter. That's 1,000 times 1 times 9.8. Subtract that from our original normal force, 56,014. 56,014, subtract 9,800. Our new normal force is 46,214 newtons per square meter. Cohesion was 1,100. Our total resisting forces, 47,314 newtons per square meter. Divide that by Our driving force, 32,340. Our new factor of safety is 1.46. We have reduced the stability of the slope by adding water. We reduced it a lot more than we did when we let the cohesion drop to 0. In other words, wet slope material makes the slope much more likely to fail than does the loss of cohesion. Our slope is much more sensitive to changes in water content, than it is to changes in the cohesion of the material. What about slope angle? Let's vary the slope angle and see how that affects the relative magnitude of the resisting and driving forces, and hence the factor of safety and stability of that slope. If we increase slope angle from 30 degrees to 50 degrees, naturally driving forces get larger, our normal force gets smaller, and as a result our factor of safety gets smaller. Let's calculate by how much. Resisting forces are given by the cosine of the slope angle. Cosine of 50 degrees is 0.643 times 3 meters of slope material times 2,200 kilograms per cubic meter times G, 9.8 newtons per kilogram. Our new resisting forces are 41,575 newtons per square meter. Add our cohesion, 1,100 newtons per square meter. We get 42,675 newtons per square meter as our new total resisting force. What about the driving force? Driving force is given by the sine of the slope angle. Sine of 50 degrees is equal to 0.766 times 3 meters of slope times 2,200 kilograms per cubic meter times G. Our new driving forces are 49,548 newtons per square meter. This number is larger than this number. The slope could not hold an angle of 50 degrees. Driving forces would exceed the resisting forces. In other words, a slope made of this material with its given density wouldn't be able to sustain a slope angle of 50 degrees because the driving force would be larger than the resisting force. Let's see how the relative size of the driving and resisting forces change if we make the slope angle smaller. Let's take it from 30 degrees to 15 degrees. Calculate our resisting forces. Resisting forces given by the cosine of the slope angle. Cosine 15 degrees is equal to 0.966 times 3 meters of slope times 2,200 kilograms per cubic meter times G, 9.8 newtons per kilogram. Our resisting forces are our normal force, 62,476 newtons per square meter, plus our cohesion factor. Our total resisting forces are 63,576 newtons per square meter, now that the slope angle has been reduced to 15 degrees. Our driving forces given by the sine of the slope angle, sine of 15 degrees, 0.259 times 3 meters of slope times 2,200 kilograms per cubic meter times 9.8 newtons per kilogram equals 16,740 newtons per square meter. Factor of safety, resisting over driving. Our factor of safety is now 63,576 divided by 16,740. Our factor of safety is now 3.79. The slope is much more stable at 15 degrees than it was at 30 degrees. At 30 degrees, resisting forces were almost twice the driving forces. At 15 degrees, resisting forces are nearly 4 times the driving forces. As a result, the slope is that much more stable. In getting ready to do your lab for this week, work through the examples that we did here in this clip. Follow the steps. Keep track of your units. Make sure that your calculator is set to degrees and not radians. Radians would return totally different values for sine and cosine. Our angles, however, are given in degrees, so we need to get sine and cosine values in units of degrees. And as you work through the example in this clip, follow along, make sure you can get the same answers we did here.